Hi everyone. Thanks for joining today. I think we are just about to start now. And thanks so much for all of you joining today, and thanks for Emmanuel for volunteering to give us some instruction today about this very interesting tool that can definitely assist in record knowledge. Um, so Emmanuel is from the Exchange program, but I'm going to hand over to him short while to give us some introduction about himself and then introduce us to what he will be giving presenting to us today. So so thanks so much, and over to you, Emmanuel. Can you hear me?
Yes, I can hear you now. Thank you very much, Rolanda, and a very good afternoon to everyone here. So my name is Emmanuel Obinyade. I'm a medical doctor and a final year master's student at the Kwame Nkrumah University of Science and Technology, specifically the National Institute of Mathematical Sciences. And as Rolanda said, I'm with the D-Exchange project. I'm with Professor Christy McKinney, Professors Peter Amwaku and then Peter Donko. And I'm excited to take us through the use of the Splink library in Python for deduplication. So I'll quickly share my screen and then we get started. So please, I hope everyone can hear me.
Yeah, we can hear you.
All right, so this will be the outline of my presentation today. Let's delve right into the topic. So deduplication is an essential aspect of data cleaning and data management that cannot be overlooked. And in today's world where a lot of data is being generated and gathered, duplicate records are inevitable. So the first question I'd like to ask is, what are duplicates? When we talk about duplicates, we are talking about records that refer to the same real-world entity that appear multiple times in a data set. And usually there are two categories. So there are exact duplicates and non-exact duplicates. When we talk about exact duplicates, we are talking about records that contain exactly the same information across all fields that appear multiple times. Those are exact duplicates. And with non-exact duplicates, we are looking at records that refer to the same individual but may contain differing information or different information. And usually when it comes to exact duplicates, you can easily remove some of them and then keep just one without causing any issues. So that one will reduce redundancy and also free up some storage. But then when it comes to non-exact duplicates, you'd have to handle them carefully because deleting one record may cause you to lose some information, which may be very important. So usually in every database or data set, there are unique identifiers that are assigned to each record. And duplicates could result in different IDs being assigned to records referring to the same individual. Usually, duplicates are caused by data entry errors, which include spelling errors, typos, manual input errors. And also variations in the formatting or the structure of the data fields could result in duplicates. System migrations, as well as information from multiple sources, could also result in duplicates within a data set. And these duplicates have several repercussions, one of which is compromised data integrity. What I mean by this is that we could have conflicting information in two records that refer to the same individual, leaving us uncertain about which record should be considered accurate. So for instance, let's say record 1 has a date of birth, which is 1st January 2024, and record 2 has a date of birth, which is 2nd February 2024. Now we are torn in between which one is the accurate one that we should select. So that's one of the effects of duplicate. Additionally, duplicates can result in increased operational costs and wasted resources. So redundant information unduly increases the volume of the data, increasing the cost of storage and even the cost of management. Apart from this, the increase in the data volume caused by duplicates could result in reduced system performance. And over here, we are looking at the time and resources required for data processing and retrieval. So for instance, if let's say you have to query a database, the query response time now increases. So overall, it reduces the system performance. Then now there's the risk of overfitting and biased models in machine learning. When you train a machine learning model on a data set that has a lot of duplicates, it can result in the algorithm learning the noise and the redundant patterns, making it difficult for it to generalize on unseen data. And ultimately, this will result in skewed and inaccurate predictions. So to mitigate these effects, we need to implement robust techniques to handle the duplicates in a data set. And there are two commonly used terms that are used to refer to the process of handling duplicates in the data set. And one of them is the word deduplication. The second one is the word record linkage. There is also a third term that's often used, which is entity resolution. And that encompasses both deduplication and record linkage. And even though their definitions are similar, each one of them has kind of a nuanced meaning to it. So when we talk about deduplication, we are looking at just a moment. We are looking at identifying emerging duplicates within one data set. So for instance, when you look at this image on your screen, you'd realize that there is the original data that has about 12 different records in there, but then most of the records are repeated. So A, B, C, and D, and they are repeated twice for each one of them. But then now when we merge those records, we now have a deduplicated data, which is what we see on the right side. And that makes the data set very clean. Then now when we talk about record linkage, we are looking at merging two or more data sets while identifying records from the different data sets that correspond to the same entity. So for instance, in this image, you can see that we are merging data sets from database A and then database B. And now we want to identify the records that are referring to the same individual, in this case, to Robin Jefferson. And sometimes the format in which the data is stored can be different. However, you should be able to identify them by employing a robust technique that would be able to fish out some of these duplicates. So for instance, over here, you see Robin Jefferson in database A, but in database B, the name was stored as Rob Jefferson. And when you check the date of birth and then the addresses, you'd also realize that the formats are different in both databases. So now what are the benefits of deduplication? Firstly, it improves the data quality. So when we handle duplicating records, errors such as fragmentation of information are handled. And when I talk about fragmentation of information, I'm referring to where we have non-exact duplicates. For instance, in health records, where let's say a patient presents on the first day and let's say on the 7th day, and the information that's gathered on both of these, on each of these days is different. So if we lose track of the fact that the patient that presented on day 7 is the same person that presented on day 1, we lose that very critical information. And so when we do the deduplication, we improve this. So I think I went off. Yeah, thank you. So additionally, deduplicating data sets enhances system performance as these data sets require less memory and processing power. And overall, it improves the performance of the systems and then the databases that handles these large volumes of data. Also, the cost of storage and management of the data is reduced, and this ensures more efficient use of resources. Finally, removing duplicates ensures more accurate data analysis, leading to better insights and reporting. And if we use the deduplicated data sets to train a machine learning model, we are sure to have very good predictions. So now we'll explore the various approaches by which we undertake this task of deduplication. So there is a first approach, which is known as deterministic matching. Over here, we identify duplicate records based on an exact matching criteria. And so what we are saying is that a complete agreement between all fields that are being compared is required for any two records to be deemed as duplicates. So let's say we are comparing the names and then the dates of birth. The name values and then the date of birth values in both records should be exactly the same for us to say that these two records are duplicates. And so over here, we are looking at being able to retrieve exact duplicates. Then now the second approach is what's known as fuzzy matching. So with fuzzy matching, we identify records that are sufficiently similar to be deemed as duplicates, but not exactly the same. And there are certain algorithms that are usually employed to be able to tell the extent of similarity between any two strings. And the commonest ones are what's known as the Jaro-Winkler similarity. Then there's another one known as the Damirao-Levenstein distance algorithm. And then there's a third one known as the Jaccard similarity algorithm. So just a brief overview on what these algorithms do. So when you pick the Jarre-Winkler similarity algorithm, it outputs a score. It compares two strings and then outputs a score between 0 and 1. That tells us the extent to which the two strings are similar. So a score of 0 means the strings are totally opposite. They are totally different. And a score of 1 means that they're exactly the same. The Jaccard similarity algorithm also does a similar thing, but uses a slightly different calculation. For the Levenstein distance algorithm, what it does is that it looks at the number of insertions or deletions or substitutions or transpositions that are required to change the value of one string to another. And in that way, it compares the two strings. Fuzzy matching can also involve the use of phonetic matching algorithms. And these algorithms assess how similar two values sound rather than how they are spelled. And usually we use these phonetic matching algorithms when we are comparing names. For instance, let me use my name as an example. My name is Emmanuel. There are people who spell Emmanuel starting with an E, and there are others who spell Emmanuel starting with an I. So a phonetic matching algorithm will just show us how the name is pronounced, and we'll be able to tell that those two names are referring to the same individual. So now the next approach is what we call the probabilistic matching. And this will be the mainstay for the rest of our presentation because that's what Splink is based on. With this, it employs statistical methods to estimate the likelihood that two records are duplicates. What it does is that it generates a probability value that shows the extent to which those two records should be seen as duplicates. I'll go more into probabilistic matching in the subsequent slides. Then the other method that's used, the other approach that's used for deduplicating records is machine learning for record linkage. Pardon me if I'm using the terms interchangeably because I wouldn't want to be very technical with the use of the words record linkage, entity resolution, and deduplication. So I'll just be using them interchangeably. So for over here, when we talk about machine learning for record linkage, we are looking at training a machine learning algorithm, which could be either using a supervised learning approach or an unsupervised learning approach, or you could use active learning or deep learning to be able to learn the patterns within the data to tell that two records are referring to the same entity. So now let's delve some more into probabilistic matching. This approach is based on Bayesian statistics principles. And when we talk about Bayesian statistics, we are looking at conditional probability. That is the probability that an event occurs given a particular condition. In our case today, we are looking at the probability that two records are duplicates given the results of our comparison. And under this approach, we predict the probability that the two records are duplicates using multiple features. And that means that if, let's say, we compare two records and we find out that the names are the same, we don't conclude that those records are duplicates. We would have to look at all the other selected features to come to a conclusion. Neither do we also reject that the records are not the same simply because the names do not match. We would have to look at all the features to now make a conclusion that these duplicates are likely, these records are likely referring to the same individual or they are not. And it's noteworthy that the probabilistic linkage utilizes fuzzy matching similarity algorithms like those I mentioned earlier, the Jarre-Winkler similarity algorithm, the Morel-Levenstein algorithm, Jaccard similarity, and can even use the phonetic matching algorithms as well. And then it incorporates what's known as the term frequency adjustments. This is one of the characteristics of probabilistic linkage. So when we talk about term frequency, we are looking at, let me cite an example to explain this concept. So when you pick a data set, there are certain common values that appear very frequently. And then there are also values that rarely appear in the data set. And so if we have two records that are being compared and we find that a rare value appears in both data sets and it's in both records and it's matching in both records, then the probability that those records are referring to the same individual should be higher than when we find a common value appearing in both records. So let me cite a very typical example. In Ghana, a name like Nebuchadnezzar is rarely given to people. So if I should see a name like that in two records, then the weight that should be assigned to that feature should be higher than if I find a name like Kwame. Kwame is a name that's given to every male that's born on a Saturday amongst many tribes in Ghana. So it's quite a common name here. If I find that common name in two records, I should penalize the weight that's being assigned to that feature, because it's likely that it's just by coincidence that two people have that same name. So now we'll go into one of the most popular probabilistic matching models, which is known as the Feligi-Santa model. And it was brought up by Ivan Feligi and Alan Santa in the year 1969. So the first thing we want to look at are the assumptions of the Feligi-Santa model. So the first assumption is that of the prior probabilities. And when we talk about the prior probabilities, we are looking at the probability that any two randomly selected records are a match. And this is represented by P of capital M or big M. There's a reason why I'm using big M, because there's another probability that we'll refer to that uses small m. So that we do not get confused, I have to say capital M and then small m. And then the second prior probability we are looking at is the probability that any two randomly selected records are not a match. And this is represented by P of big U. And these two probabilities are actually complementary. That's how come you can see that I've written that P of big U is equal to 1 minus P of big M. Then now the second assumption is the conditional independence of features. So every feature that's selected for comparison in this model must be independent of the other. For instance, if a data set has two columns, one that has just the first names and then another one that has full names, we cannot use both of them for comparison, because the column that has the full names already has the first names in there. So we can't use both of them since they are dependent on each other. Then the third assumption is the posterior probability assumption. That's the updated probability that two records that are being compared are matched based on the current comparison results. So let's look at the assumptions this way again. First of all, we estimate a prior probability, the probability that if we pick any two records randomly from the data set, there will be a match. Then now we select features that are independent of each other. And after we've gotten our comparison results, we now update the probability for the two records under consideration. So those are the assumptions of the Feligi-Santa model. Now, the Feligi-Santa model employs what's known as the expectation maximization algorithm to estimate some of the key model parameters. And we may not be able to go into all the mathematics of this expectation maximization algorithm, but it's an iterative algorithm just like the popular gradient descent, and it finds optimal model parameters when it converges. So that's all I'm going to say about this. We'll just move on and talk about how the Feligi-Santa model works. So the first thing is that we estimate a prior weight, and this is derived by calculating the probability that two randomly selected records are a match. And then we take the log2 of this probability value to get the weight. The reason why we take the log2 of this value is that usually in every data set, the percentage of records that are duplicated are very low. They tend to be very low. They're estimated between 1% to about 5%. Unless the data wasn't handled very well, then that's where they may blow up beyond proportion. But usually they lie between 1 to 5%. So when you estimate that probability, you're going to get a very low score. And finding the log2 of that number will give you a bigger number that you can easily use for your computations. So after we've estimated this prior starting weight, we now carry out the comparisons. And the comparisons are usually carried out in a sequential manner using a multi-level approach. So we have the first level, which is, let's say, an exact match. Then we could have multiple levels of partial match. And this is usually based on a fuzzy matching algorithm with different thresholds. So let's say the first level could be an exact match. The second level could be a Jawara-Winkler similarity, which is greater than 0.9. The third level could be, let's say, a Damerau-Levenstein distance, which is less than or equal to 2. Then now, usually the final level would be a comparison where there is no match between the two strings based on the initial comparison levels that we have stated. For each comparison level of every feature, so we are comparing on each feature. Let's say we pick the name, we compare, the dates, we compare, we pick the address, and then we compare. On each level of each feature, we are going to generate two probability values. And the first probability value is the small m probability. This is the probability that the feature matches in a record pair, given that the records are a true match. And then we also calculate the U probability. That's the probability that the feature matches in a record pair, given that the records do not match. So for instance, if I have two records with the names in both records being Kwame, what is the probability that the names are the same by coincidence? If the names are the same by coincidence, then that's how I would derive my U probability. But then if the names are the same and both records are also referring to the same individual, then based on that, I'll be able to derive my M probability. So it does that for each level. So apart from it, the algorithm looking at it in terms of an exact match, it can also come and look at it in terms of the Java-Winkler similarity. So if the similarity between the names in both records are more than 0.9, then what's the probability that they are referring to the same individual? And if the similarity is also greater than 0.9, what's the probability that this was just by mere coincidence? So these are the two probability values that we estimate for each feature on each level. Then now, the probability values that are generated, we now find the log2 of these values to generate what's known as the partial weights. And so they are assigned to each comparison level. And when you compare any two records, on whatever level that they agree on, you assign that weight to those two records. And so we realize that the partial weight from each feature represents the evidence provided by the comparison on that feature, which either supports or opposes a match status. And then the prior weights, when we are done with all of these comparisons and we've assigned all the weights, now we sum up the prior weights and then the partial weights that are generated on each feature for the two records under consideration to now produce a final score that indicates whether the record pair that we are looking at is a match or not. So you'd see that I've written a formula here. Final match weight will be equal to the weights, the prior weight. Then now let's say we have 5 different features. Then we sum up the weights on each of these features to now generate a final match weight. So let me talk just a bit about Splink, and then we go into a very typical example to understand what's going on. So for Splink, it's a Python library that employs this Felici-Santa model for probabilistic record linkage. And the beautiful thing about it is that it has a very intuitive graphical output that illustrates exactly how the model predicted that a record pair is a match or not. And we'll see those graphical outputs as we run the code. One of the advantages of using Splink is that it's easily customizable. So irrespective of the kind of deduplication task that you want to undertake, you can customize the settings. You can tweak the parameters of the model to be able to undertake those comparisons for you to deduplicate your data set. And it's also designed to handle large data sets in a very scalable way. Actually, it's optimized for cloud computing. So it's able to leverage distributed computing to handle large data sets in record time. So let's look at this example in here. We have a data set that has just 2 records and has 5 features. So we have the full name, the date of birth, social security ID, street number, and then the postcode. And the name in here is Hawa Isaku in the first record and Hawa Isahaku in the second record. So what we're going to do is that we are going to compare both records on each feature. So the first thing is we compare the records on the full name. There's Hawa Isaku versus Hawa Isahaku. And the level of agreement was a Java-Winkler similarity level, which is greater than 0.9. That means if you are talking in terms of percentages, it means that both names are over 90% similar. Then now we look at the dates of birth, and we realize that the dates of birth are very, very different. So they are categorized as no match. Same for the social security ID. And then when we look at the street numbers, we realize that they've been categorized as an exact match because they are the same, 25 versus 25. And for the postcode as well, it was categorized as an exact match because they are the same thing. So this is one of the graphical outputs of Splink. And this chart shows the match weights that were generated for each level. So as you can see on top here, there's the prior or starting match weight, and it's around minus 10 point something. Then now there's a weight that's generated for each level. So for instance, when we pick over here, we've labeled it as the name tokens, and it refers to the same as, it refers to the full name of the individual. So for the full name, if they agree on an exact match level, a weight of around 10.2 is assigned if the Levenstein distance is less than or equal to 1, that means that it was just one character that was probably inserted or that was deleted or substituted, or there was a single transposition. It corresponds to a match weight that's around 10.2. So same thing is done for all of these levels. And then now it outputs another graph over here that shows a comparison for 2 records under consideration. So you'd realize that the starting weight on the left side, first of all, let's look at the x-axis. You'd realize that the x-axis has the various features in there. And then the y-axis on the left side outputs the match weight. And on the right side, the corresponding probability value. So that would be more intuitive for us to understand. So when you look at the prior weight, there's a weight of minus 10.89. Then for the full name, Hawa Isahaku and Hawa Isahaku was 7.64. And as I mentioned earlier, there is what's known as the term frequency adjustment that's applied if the name is common to penalize the weight on a feature if the main feature is common, or to add extra weight.
Okay, funny. I think Maya might have dropped off. Let's just wait for him to reconnect.
Sorry, I think I lost connection.
Yes, no problem.
So I'm back online now. Let me quickly share my screen and then we continue from there.
Okay, great.
Okay. So
Emmanuel, I think we were at maybe that one. Yep.
okay, good. So let me continue from here. So I was saying that one of the graphical outputs of the Splink model is that it outputs this match weight chart. And with this, we can see the prior starting weight in here that was generated from the whole data set. And then now on each level, a certain match weight is assigned so that if 2 records agree on that level, that match weight is assigned to those records. So what we do is that there's what's known as a comparison vector that's generated. It's a vector that contains the values of agreement of the fields for each record pair that's being compared. I hope that wasn't too much to take in. So let me just go over that again. So for instance, if let's say I have 2 records and I'm comparing them on their names, if they are an exact match, I assign a value, a match weight, this match weight that was assigned to exact match to those 2 records, and I write them in a vector. So all those values are stored in a vector, which we call the comparison vector. And at the end of the day, we sum up all the values that we were able to generate in the comparison vector for the 2 records under consideration to now get the total match weight with its corresponding match probability to tell us the extent to which those 2 records are similar. So this is the match weight chart. Then from there, for every 2 records that you compare, you can output this waterfall chart that shows you exactly how the model concluded that those 2 records are duplicates or rejected that those 2 records are non-duplicates. So for instance, in the record, in the data set that I showed, that's Hawa Isaku versus Hawa Isahaku. This was the waterfall chart that was generated for those 2 records. We have a prior starting weight, which was minus 10.89. Then we have a full name weight that was generated 7.64. And I mentioned earlier that one of the characteristics of probabilistic matching is the use of the term frequency, which looks at how common the term was within the data set or how rare the term was within the data set. So in my initial example, I used something that was generally common and generally rare. But then you could have a name that's very common in real life, but then when you look at that data set, it's a rare value in the data set. So when you see those two names matching, the model goes through the whole data set to be able to tell that this value in this column is rare or is common. And there's a whole calculation to find the amount of weight that should be either added or subtracted from the initial partial weight that was generated based on the commonness or the commonality and then the rarity of the value. So that's the match rate that was generated here. Then for the dates of birth, there was another match rate here. And because this was on the level of no match, it generated a negative score. The same for social security ID. Usually, if there's no match, there's a negative score that's generated. But then when we get to street number, we realize that the street numbers are the same. So there was an exact match. And when the model looked through the data, I realized that the street number 25 was a rare value. And so added some more weight to that street number because it's most likely that if two people lived on that same street, I mean, it's most likely that if we have that same street number in two records, it's referring to the same individual. So there was an additional weight that was added. Then when we look at the postcode, it was 3188. However, when the model looked through the data, I realized that the postcode 3188 was quite common. And so penalized it to a certain level by subtracting minus 1.35 from the match weight that was assigned to it. And now the final match score was 5.72, which corresponded to a probability value that was almost 0.98. So let's say it was around 0.97. So for these two records, we are 97% certain that they are referring to the same individual. So that's how Splink works. So we'll now, okay, before we even go into the demo, there is usually a workflow for doing a deduplication task. Usually we start with data cleaning and pre-processing. Even though the whole task of deduplication is a data cleaning task, there's an initial data cleaning and pre-processing that's done mainly to standardize the formats so that now when we compare two records, we would not have a lot of misleading results. We wouldn't have a lot of false negatives, especially because there are times that the dates could be written in the format of year, month, and day. And in another record, it could be written as month, day, and then year. So you'd have to standardize the formats. And that's where the initial data cleaning comes in. Then now there's what's known as blocking. Over here, we filter out a subset of the whole data set. When you pick any data set and you have to compare each record against every other record to be able to tell which ones are matches, the number of comparisons that we would have to do increases quadratically. So for instance, if we have a data set that has 5,000 records, we'd have to do about 12 million comparisons. And that would really be unnecessary, especially because most of the records may not have anything in common. So we do not need to compare them. So we filter out a subset of the records that have a bit of a similarity, just some level of similarity based on certain rules. And then now we compare those records and we are likely to find records that are referring to the same entity within this block of the data set. So after blocking, we now do the comparisons, and afterwards, based on the results that we get, we can classify them into duplicates or non-duplicates. Then finally, after we found our duplicates, we can now group all of them together. All the duplicates that refer to the same entity can now be grouped. So we would have a number of clusters in the data set. All right, so let's go into the demo to see how exactly Splink works. Okay. Let me stop share and then share the Google Colab. Just a moment. Okay, great. So we are now going into the code proper. So the first thing we want to do is to install Splink. And in this tutorial, we're going to use Splink version 3.9.14. So the current version of Splink is the version 4, which was released just about a month ago. And the features are slightly different from 3.9.14. However, if you do any deduplication task in 3.9.14, you can easily transfer the code into version 4. So we could still go through this and then have a very good grasp on how Splink works. So if you are in terminal, you can just type pip install Splink is equal to 3.9.14. If you are working in a Jupyter notebook, you can just use this bank command, which will also allow you to install what's in terminal. So I've already installed this, so we could just move on. Let me just put that. Yeah, great. Now we are going to import our libraries. So we import pickle, we import regular expressions, and then from splink.db.linker, we import the DACDB linker. Splink is mainly based on SQL and then Python. So, and it uses the DACDB SQL. So that's how come we need to import the linker from there. And since we are dealing with a data frame, you can't handle data frames without using pandas in Python. And now we are going to import the data set we are going to use for this tutorial. Please, I hope you can see my screen. Hello?
Yes.
Okay.
Yes, we can see your screen.
Then we import NumPy. And if you want to generate some interactive graphs, you could import Alt, but in this case, we may not really use it. You can explore that. It has very nice graphs in there. Then we import the comparison library, which is a default library in Splink. And there's another default library, which is known as the comparison templates library. We import it as CTL. In Splink version 4, both libraries have been merged together. So you only have to import the comparison library. And every comparison that you'd have used CTL for, you can use CL for. Then now we load our data set. So this is the freely extensible biomedical record linkage data set, the third version. So it's a data set that's usually used for record linkage. After loading it, we just want to view the first 5 records in there. As a data scientist, you need to see what your data contains. So we call the .head method on our data set, and then this is what we see. So we can see that there's a rec ID, given name, surname, street number, address 1, address 2, suburb, postcode, state, date of birth, and then the social security ID. But then we want to know how many records are in the data set. So we call the shape attributes on our data sets. And we also want to know the data types in there. So we call the .info method on it. So over here, we see that we are dealing with 5,000 records, and there are 11 different columns in there. Then now when we look at our data types, we have 2 of the columns being
Hello,
in
Emmanuel.
Yes, hello?
The screen is not moving.
Oh, can you see?
We see only the pip installation, the cell for the pip installation. That's
Okay.
all.
Yeah, I'm moving. Just give me a moment. Let me share the VS Code instead. Just a moment. But when we are done, I'll share the Google Colab. It's the same thing. Yeah, I think so. All right, please, can you see?
Yes.
Okay. Is it moving now? Yeah, I think it is.
Yeah, it
Yeah,
is.
now it's
Okay.
better.
Great, great. So now we call the .info method on our data set, and then you can see that there are 9 object data types in there, and then 2 in 64 data types in there. One thing about pandas is that if there are mixed data types within a column, it usually refers to it as an object data type. So you'd need to, if you are very particular about the type of the data type in that column, you'd have to call that particular data type on that column. So now we want to see how the columns have been listed. And you'd realize that there's a space in front of every column name in here. So we need to handle that. Otherwise, when we want to call the columns later on in our code, we may have difficulties because you would not likely remember that there's a space in front of it. So the first thing we do is that we apply the .strip method on the column names to remove the leading white spaces. What the .strip method does is that it removes leading and trailing white spaces. Then now, when you look at the data set, let me scroll up a bit. You realize that this rec ID column has the record ID in here, which is unique for every record. However, there are some commonalities in there. So this is record ID 1496-ORG, which means this is the original record. And then you could see another record here, which has DUP3. That's the third duplicate. And because we are using this to learn, this one has labels. This data set has labels. But usually in real life, you wouldn't have a data set that has labels. But then when you use a data set that has labels, you'd be able to know how your model is working. And then later on, you can apply it on a data set that doesn't have any labels. So we are going to extract this number in here because this will be a common value in every data set that's referring to number 1496. And that's what we use as our label column. So I'm going to refer, sorry. Okay, I think there's a question on the library installation. Just a moment. Am I still in Zoom? Am I still online? Okay, I can't see my Zoom. Anyway,
Yes,
I'll answer the question. All right.
you are online.
Okay. So let's continue from there. So we're going to do a bit of data processing. As I said, we want to get the labels column. So we refer to that labels column as rec. And then now we split the values in there using the hyphen as a delimiter. And usually the number in there would be the second part after you've done the split. So we just extract that number. Then now, as I mentioned earlier on, when you have the object data type, it could be mixed columns. So for instance, for the dates, we want to really specify that we want them to be strings because you could have dates that are integers. So we now call the as type, and then we convert it to a string, and then we apply the .strip method also on the values in there to remove every leading and trailing white space. Then now for some of the values that are missing, pandas may not see them as missing values. We'll just see it as an empty string. So you need to assign it as a missing value. So that's what we do here on this line. We do the same thing for the social security ID and then for the postcode. Then now, for the sake of this presentation, we wanted us to see how we can engineer some features. So we want to create another column which has the full name. So we add the given names plus a space and then the surname to have the full name. And that's the value that we'll see in the full name column. When we are done with this, we want to see how our data set is looking like. So we call the dot head to see just the two values. And we can see that there's the full name column to your right side over here. Then now, in most data sets, what happens is that sometimes when people are filling in their names, they do not really take notes of the order. So if let's say they were supposed to write the first name first before the surname, there are times that they could write the surname before the first name. And when it's being imputed into the data set, it would be written in that same order. So if you don't take care, you might miss out on duplicates that have such a discrepancy. So we would want to reorder the names such that the names are in alphabetical order. And we refer to this as tokenizing the names. So now we create this function in Python, where first of all, we check that the value in the data set is not a missing value. And then we return a sorted set of those values. So that's what we apply on that column. So in Pandas, if you want to apply a function on a column, you use the .apply method, and then you call the function. So we apply that on the full name column. This time we are labeling that other column as full underscore name. Now we want to see whether what we did really worked. So we call the .head method again, and then we can see that over here we have the full name. However, we are seeing that it came as a list, and it also has comments in here. One thing is that mostly punctuations affect the string similarity algorithms because they read punctuations also as characters. So the fact that there's a punctuation means that it could result in some misleading conclusions. So as much as possible, we want to take out every punctuation unless domain knowledge doesn't allow for you to take out the punctuations. But as much as possible, we want to take all of them from our data sets. So the first thing, because this returned a list, we now have to convert it to a string. That's how can we do this over here. So .as type string. And then now we want to clean the punctuations in the full underscore name column Over here, we are going to use regular expressions. So regular expressions are patterns that are used to search and then match strings in a data set. And they can also be used to manipulate data within a data set easily. So what we do is that we compile a certain pattern. So this is an R string. And the pattern in here simply means that whatever character in there should not be an alphabet and should not be a space. So if we see any character that's not an alphabet and not a space, so let's say if we see a punctuation, if we see a number, we should bring that record up. And then the second pattern that we are looking at here is that there shouldn't be two spaces. So if we see anywhere for any value, if there are two spaces, it brings that record up. Then now what we do is that we replace those values. That this remove punctuation here is the pattern up here. So we replace those characters that are not alphabets or spaces with nothing. And afterwards, we replace the multi-spaces with one space. So this one is one space in here. We replace it with one space. Now we call the function on the full underscore name column. Finally, we take a look at our data set and you'd realize that over here, the punctuations have all been removed. So we just have the names, the spellings of the full names in here. So our data set is now set for us to undertake the comparisons. Now we are going to create our linker object in Splink. This is where we are about to implement Splink proper. So the first thing is that the settings is usually set up as a dictionary. So we have a key here and then we have the value in here. So the first key in here is the unique ID column name. And for every data set, as I mentioned earlier on, a unique ID is generated for every single record in there. And those unique IDs never repeat. So we have this unique ID in here, which is in the rec ID column. Then now for the linkage type, because we are deduplicating one single data set, we type in dedupe only as the value for the link type key. If we were doing a record linkage, that's merging two data sets and then handling the duplicates, we'll type record linkage and dedupe only, record linkage and dedupe for the link type. Now we initialize the linker object. So that DB linker, you can just initialize the linker object using the data set, or you can initialize it using the settings dictionary as well. So this is our initial settings dictionary. We are going to update the settings dictionary as we go on. So Splink allows you to do some extra exploratory data analysis. So the first thing we do here is to check the missingness chart. We want to see how many columns have missing values in there. And this is an output that was produced. Splink uses Alt-A for its graphical output. So with Alt-A, it's interactive. When you hover your cursor over the graph, you can see certain values in here. So we can see that the column is date of birth. The null values are 155, and it constitutes 3.1% of the whole data set. And the total record count is 5,000. And that's the only column that has some missing values in here. Apart from that, we can also generate the profile columns in here. And this one gives us the number of missing values, the number of distinct values, then the top 10 values by count, and then the bottom 10 values by count as well. So for our unique ID column, we are supposed to have each of the values being just one. So we want to check that again to make sure that that's what we are having in here. And there are 0 missing values in here, 5,000 distinct values. Now for the given name, we have 0 missing values, 1,214 distinct values. And then the top 10 values, we have one of the names over here. This name is a missing value, so we had to handle it. Then this other name, Joshua, appears 81 times, and the bottom 10 values only appear once. You can do the same for all the other columns. One thing is that in deduplication, according to literature, if the missing values in a particular column is 30% or more, it's advised that you do not use that column for the deduplication because you are likely going to get misleading conclusions. So now we move on to our blocking, where we are going to filter out a subset, and we are going to use certain rules. So the first thing is that we check to see if the social security IDs are the same. Let's filter that block of records out. Same for the given name, surname, date of birth, and postcode. And now we could generate the cumulative number of comparisons based on these 5 blocking rules. So when you hover your cursor on this graphical output, you'd realize that the SQL condition was the left side should have a social security ID, which is equal to that on the right side. That's the left record should be equal to the right record. And we're able to generate 5,601 comparisons. And this Cartesian product of input data simply means that's the total number of comparisons that are generated if every record is being compared against every other record. So same thing for the given name, 48,000. Cumulatively, we now have 54,000. Now let's come to the last part, and we see that the last SQL code was the postcode on the left record should be equal to that on the right record. And it generated 11,000 comparisons. And cumulatively, we now had 102,000 records that we are going to compare. Now we are going to update our settings dictionary. So apart from the unique ID column name key and then the link type key, we're also going to pass the blocking rules value to the blocking rules to generate predictions key over here. And because initially we assigned our blocking rules to a variable, we can just write it in here. Ideally, we were supposed to come and write this list up here. That's the blocking rules in our settings dictionary, but you can write it outside and assign it to a variable and just pass it to the settings dictionary so that it doesn't look haphazard. Then now our comparisons. This is where we are going to specify exactly how we want the records to be compared. So over here, we are going to employ the name comparison in the comparison templates library, which is a default library in Splink. And we are comparing the full name, and we want the term frequency adjustments to be applied in there. Then now we also compare the dates here. So there's a date comparison setting in the comparison templates library that we use. So we look at the date of birth column, and we do not want to check the Demirel-Levenstein distance threshold. So we do not assign any value to it. But then we cast the strings to a date time object. Then invalid dates should be seen as now. So there are times that you could have a date written with, let's say, 39th February or maybe 41st January, and those are invalid dates. So when you cast the strings to date and now you type in your settings that the invalid date should be seen as now, that date would now be seen as a missing value. Then we specify our date format. That's the year, month, and then the day. Then now we specify how we want to compare the social security ID. So we want to use the Demirel-Levenstein distance threshold of 2. That means there should be at most 2 insertions or deletions or substitutions or transpositions. Then for the street number, we want an exact match. If it's not an exact match, then it's no match at all. Same for the postcode. And now we retain intermediate calculation columns as true. And the reason for this is that when the EM algorithm, that's the expectation maximization algorithm, is being run, Splink allows a maximum of 25 iterations. And sometimes by the time it hits the 25th iteration, the values wouldn't have converged. When you set up your settings dictionary to retain the intermediate calculations, whatever value that it gets by the 25th iteration is what will be used. And sometimes it still works. So we'll just keep it as such. Then now we instantiate our linker object here with this updated settings. So let me uncomment out this block of code and then talk about it. The beautiful thing about Splink is that you can easily customize the kind of comparison you want to undertake. And as I said, even though it has its default comparison library, you can specify how you want to compare the records. So over here, you'd have to be explicit and write out a bit more code than what you'd write in the initial settings dictionary. So the initial key value pairs are the same. So unique ID column remains the same, link type, blocking rules remain the same. But then when we get to the comparisons, so let's say we didn't create the full name column and we wanted to compare the given names against each other, as well as comparing the given names to surnames in cases where we think someone may have written a given name under the surname column or a surname under the given name column. We can specify it here. So the first thing is to handle the null values. And as I mentioned earlier on, Splink is based on SQL and then Python. So you have to write the SQL condition, then you write the label for the charts, which is null, and then you write the null level, which is true. Now you can come down here and then specify that you want the given name on the left record to be the same as that on the right record. Then you specify the label for the chart. That's exact match, given name, and then 1.0. That's for the TF adjustment route. Then we do the same for the surname. Then over here, if we want to swap the matches, so we want to now compare given name against surname or surname against given name. Usually when you use the default libraries, it can't compare values in two different columns. You'd only have to specify one column. So if you want to compare values in two different columns, or let's say even in three different columns, you can now specify it yourself by explicitly writing out how you want the comparison to be done in here. So that's what we see here. So over here, we have the Damerau Levenstein distance, same here. For the Jarrow-Winkler similarity, ideally supposed to compare values in the same column. So over here, supposed to compare values in the given name. But then now we want to compare the Jarrow-Winkler similarity between surname and given name. So we specify it here, and our threshold is 0.9. So for this dictionary, I'll now comment that out again. You can explicitly write exactly how you want it to be compared. Even for the date comparison, so the default date comparison in Splink checks whether the dates are an exact match, checks whether the two dates are 1 month apart, whether they are a year apart, and whether they are 10 years apart. If you do not want that and you just want to compare the dates in a different form, you can specify the SQL conditions yourself so that it uses your comparison. Because there are times that your data set requires a certain comparison that's not a part of the default Splink library. And so you can specify that out yourself. Then now we would have to estimate the prior starting weight. And with that, we use some deterministic rules. So the first thing is that we want to check whether the social security ID on the left is the same as that on the right. Then now, whether the given name on the left is the same as the given name on the right. And then the surname on the left should also be the same as the surname on the right. And then the date of birth should be the same as the date of birth on the right side. So this is one condition. And all three of them must agree before that record would be picked. Then we can also do the same thing for given name against surname against given name, and date of birth in both records. So these are the deterministic rules. And that's what we are going to use to estimate the probability that when we pick any two randomly, if we randomly select any two records, they are likely to be duplicates. So we want to use a deterministic rule to be able to tell this. It's just giving us an estimate of how many records we should expect to match within our data set. There are times that you could use very loose deterministic rules. So let's say we could use maybe just given name against given name in the left record against the given name in the right record. And that would be very loose because mostly first names are usually very common. Most first names are very common. So you are going to get a large number of records being seen as duplicates. However, you could also use very strict rules like what we've used in here. And if your rules are extremely strict, you'd have very few values in there. And this probability, the probability that any two randomly selected records are a match, is what usually Splink uses as its default threshold. But then by the time you go through you run through the whole model, you can set your own threshold. So after we run this code, it outputs that the probability that two random records match is estimated to be 0.000528. And this means that amongst all possible pairwise record comparisons, 1 in 1,894 are expected to match. And so with 12 million total possible comparisons, we expect a total of around 6,595 matching pairs. By the time you are done with your comparison, you should get a number that's close to this, or maybe more than that. And as I said, depending on the strictness of your rule, you could get a small number here or a large number there. And that would not be so accurate. Then now we estimate the U probabilities, which is the probability that two records match on a feature, given that those records are not duplicates. And with that, Splink usually uses random sampling instead of using the expectation maximization algorithm. And this is because we know that for every data set, most of the records in there are not likely to be duplicates. So if we pick a random sample, we are almost certain that most of them would not be duplicates. And so based on that, we can estimate the probability that two records would match and yet they are not duplicates. Instead of using the expectation maximization algorithm, which may be a bit computationally expensive, especially if your data set is very huge. So we run that and then we get the U values. Then now for the EM algorithm, we need to specify some blocking rules, deterministic blocking rules actually, that will be used to estimate the M probabilities. And it's because we want to know the probability that the two records are a match, given that they match on a particular feature. So now we pick the date of birth here, and we only use the first to the third values in there. And then for the postcode, we use the first and second values. Then now we run the expectation maximization algorithm, and it's able to generate some values for us. So it runs and then it tells you that your model is either fully trained or not fully trained because certain values were not estimated. And you'd have to go back to check your settings dictionary to be able to work on that. So afterwards, it outputs a match weights chart. Over here, you'd see that these were the match weights that were generated. So for the prior starting weight was minus 10.88. For exact match was 10.836. So it shows you the M probability. First of all, it shows you the comparison name, the label, the SQL condition, the M probability, the U probability, and then there's a calculation of what's known as the base factor, which is simply M divided by U. And then now we find the log 2 of that value. And that's how come we had 10.836. And it's the same thing for the Damirel-Levenstein distance, Java-Winkler similarity, and then a similarity, Java-Winkler similarity greater than or equal to 0.9, and then a similarity greater than or equal to 0.8. And then finally, one for no match status. And usually that's a negative value. So when you check the date comparisons as well, weights have been generated for all of them. Then now, based on these weights, we are going to predict on our data. So we run this code. When you run the predict method on the linker object, you may either specify the match probability threshold or not. If you do not specify the match probability threshold, it's going to compare every record that was generated from the blocking rules. However, if you specify the match probability, it would only output probabilities that were 0.1 or above. That's the threshold that you specified. It will only output probabilities that are either at the threshold or above the threshold. Then when you get the results, you can now render them as either a pandas data frame or as a dictionary. And the dictionary is what we will pass to the waterfall chart. So let me go over this match weight chart and then the waterfall chart. This match weight chart over here tells you the weights that were generated for each comparison level. And that's not based on the two records that are being compared. But then when you look at the waterfall chart is looking at two records. So for two records under consideration, how was the final match score generated? So that's the difference between the match weight chart and then the waterfall chart. So if you want to look at your results as a data frame, you just render it as a pandas data frame, and you can look at how the you can look at how the duplicate status was determined. So we can see the columns in here, the match weight that was generated, the probability, then the record ID on the left, and that's on the right. The full name on the left, and then the full name on the right. Then there's this gamma level, which shows the level of agreement in the match weight chart. So for instance, over here, there's Jake Westbrook for the full name on the left and Jake Westbrook for the full name on the right. And it generated the gamma level of level 4. So let's go up again. Just a moment. So when you check the full name column in here, you realize that this would be level 0. This is level 1, 2, 3, 4. So if it assigns a gamma level of level 4, it means that the full name column in both records agreed on this level 4. If it assigned a gamma level of level 0, it means they agreed on the no match status. There are times that I can assign a gamma level of -1, and that means that there was a missing value in there, or the format was not standard. So for instance, as I mentioned earlier on, if let's say a date contains something like 39th January, that's an invalid date. So we can't use that for comparison. It would output a gamma value of -1. So that's the interpretation of the gamma values. Then now we have the term frequency and then the base factor, which I've already explained. So apart from rendering it as a pandas data frame, we can also render it as a record dictionary. and the record dictionary can be passed to the waterfall chart. So for instance, when we rendered this as a pandas data frame, it gave us 6,506 records. Over here, we can generate 6,506 waterfall charts, but then it will take some time. So we just want to view just about 4 of them. So we generated from 240 to 244, just 4 waterfall charts. And we could just go through them to see how the final score was generated. So over here, we see a name Callum Janux and Callum Jankus, which has a Demirel Leverstein distance of less than or equal to 1, because U and K in the first name was transposed in the second name. So this was the weight that was assigned to it. And because they are not the same, we couldn't calculate the term frequency. We checked the dates of birth. And then we see the comparison that was done on it. Then the same for the social security ID, the street number, then postcode. And finally, we realized that a match weight of 6.65 was generated. So when you check this date of birth, you'd realize that because there was a null value, that's how come no weight was assigned to it. I mean, because the date was invalid, if you look at it very closely, you'd realize that the date was 1990, 3925. And there are no 39 months, neither are there 39 days in any month in the year. So because it was an invalid date, it was seen as a null value. We can scroll forward to see. So this one had a null value in there for the dates of birth, but then the comparison on first name was Hendrix Isabella. So for every single pair of records, you can look at how the comparison was done. And this makes it easier for experts to do clerical review when it comes to record linkage, because clerical review is a very integral part of record linkage. So you could just go through all of them. And then finally, because we had a label column in this data set, we can now check the precision of our model and how well it's working. So we generate an ROC curve, and this seems to be working very well. When you hover your cursor on this ROC curve, you realize that if we apply a threshold of 63%, we're able to get 6,452 true positives. That's the TP. And then the true negatives are 95,979, no false positive, and 86 false negatives. If we reduce it a bit to a threshold of 44, we are generating 6,478 true positives, no false positive, and then a false negative rate of around 0.00, because we generated just 60 false negatives. It just gives you an idea of how your model is working. Then finally, you can check the errors that were being predicted from your data frame, and it will tell you why those records were not picked. So the first thing you see is that you'd have to know whether they were found by the blocking rules or not. And if you realize that your records were not found by the blocking rules, you could look through them to see where they match, and then you could now update your blocking rules so that these records would be picked. The only challenge is that in real life, the data sets do not have labels, and so you'd find it a bit difficult to generate this errors data frame. However, if you have labels like what I do, then you can do that. And that one can also be expressed as a record dictionary here. The last thing that we do is the clustering, where we are grouping records that refer to the same individual into different groups. So we call the cluster pairwise predictions a threshold method on the linker object. And based on our results, that's the predictions that we did earlier on, we now pass those results as arguments to this method, and then we specify the threshold match probability. So we can specify it as 0.2 or 0.5, whatever we want to, however we want to specify it, we can do that. Then now we can now create an HTML file that will show you how they look like. So usually they are represented as graphs, and where the records are shown as nodes, and then the similarity value in between any two records is shown as an edge for easier visualization. So you can do that. We run this and then we generate a Cluster Studio tutorial HTML file. Quickly, let me just show that one. That's the last thing I'm doing, and then we'll be done. Then we probably will take questions. So let me just share that in a moment. Okay, great. So this is the HTML file that it generates. Over here, you can see that these records are shown here as notes, and then the edges in between the graphs are shown in here. That's the similarity score. So when you hover your cursor over an edge, it shows you the two records that are being compared, the names in there, the dates of birth, the social security ID. That's basically the features on which they are being compared, and then shows you the match probability between the two records, and then the match weight. So right here, we see that the match probability between these two records is 0.99, and the weight is 35. Same for these other two. It's similar. You can increase the threshold by dragging this up here, or you can reduce it. And if the match probability is lower than the threshold that you set here, then the edge will be taken out. So usually when we cluster them, it's to aid us to know the areas we should look out at for false positives or for false negatives. So basically, this is how Splink works. There is more functionality to it, but this is how far we can come. Thank you so much. I think I would open the floor for questions now.
Thanks so much, Emmanuel. Yeah, some folks I've dropped off, but I think there are still a few questions. So Steph has mentioned that it would be great if you can share the presentation and your code after with the rest of the group, if it's possibility.
Sure.
And I think Seth also commented about the comparison between a tornado diagram and a waterfall chart. I don't know if you want to comment about that, if you know of. It's not related to the Splink library, but if you can comment maybe about differences on there.
Yeah, so I could just answer that quickly. So for the linker match weights chart, it's showing you the weights that were generated for each feature, for each level of each feature. But then when you look at the waterfall chart, it's showing you how two records under consideration were considered to be duplicates or non-duplicates. So it shows you the values that were generated for those particular two records for us to get the final match weight on those two records. But the linker match weight chart is on the columns and then the various levels of comparison. I don't know if I answered the question. Hi.
Okay. That's fine. So if you can answer now. Are there any other questions for Emmanuel? Andre is just saying, thank you so much, Emmanuel, for this great presentation. It is very interesting. I agree. It was very interesting. I never knew that there could be such complex analysis done on trying to find duplicates. So it's really informative for myself as well.
You're welcome, and thank you for the opportunity as well.
No other questions. I think Emmanuel is also welcome to answer questions over email. Is it okay if we will share your contact with the group later on?
Sure. That's fine.
All right. So if there's no more questions for Emmanuel, I really want to thank you for today. Informative eye-opener for a lot of us. And I could see folks were very, very much glued to the screen. So really thanks for that. And yeah, happy to see your publication output from this soon. All right. Thanks everyone for joining as well. It's really good to have such a big audience on this demo series, and we hope to see you again on the next webinar. Thanks so much, everyone. Have a good day further. Okay. Right.